Okay, welcome back. In the last video, we talked about the general definition of a vector space. And we saw that a vector space is, by definition, just any set whatsoever, together with operations called plus and times, called vector addition and scalar multiplication, that satisfy 10 properties. These are called the axioms of a vector space. And any set whatsoever with those two operations, and those operations can be defined however you want, as long as those 10 properties hold, that set, together with those operations, is called a vector space. So a vector space is a set with the operations, and the operations satisfy certain natural properties. And the topic of linear algebra is essentially the study of vector spaces. So not just R to the n. Now we've seen that if F is any field, then Fn is a vector space over F. But there are more examples. And in this example, we're going to look at, in this video, we're going to look at examples of vector spaces that are subsets of Fn. So this leads to the concept of a subspace, which is what we're going to talk about today. So subspace. So here's the definition. Suppose that you have a vector space V plus dot. So let this be a vector space. Now how come I didn't just say let V be a vector space? Well, because by definition, a vector space consists of not just the set, but also the operations. And so it's really these three things together, right? These three things together are the three ingredients that you need to have a vector space. And so technically a vector space is really a collection of these three things, not just the set V. Okay, so let this be a vector space, then say over a field F. Well, every vector space is over a field. When we say let this be a vector space over a field F, what we really mean is, let F be the field that the vector space is over. So let V be a vector space over F, a subset. So we want to define the notion of a subspace. Now a subspace is a certain type of subset of V. A subset U in V is called a subspace of V if U plus times is itself a vector space. Let's explain what's going on. So you have some vector space V, okay, and you have some subset U. Now whenever you have a subset U, right, the elements of U are in particular elements of V, because U is a subset of V. So if you have elements in U, you can add them together. Now, if you just have a random subset U of V, and you take two elements of U and add them, you're going to get a vector in V, but the sum might not be in U. And if you have, similarly, an element in U, and you scale it by some scalar, the scalar multiple, the result, might not be in U. Of course, it's going to be in V, because V is a vector space. But if U is not a vector space, then you could very well scale a vector and get a result that's no longer in U. So if the set U, together with the addition and scalar multiplication, is itself a vector space, we call U a subspace of V. Now let's take a look at an example before we go to the general theorem about how to tell if a subset is a subspace. So we have our field F, and consider just the general system of linear equations. Consider the system of equations over F, which is a11x1 plus dot 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 plus a1nxn equals 0, and am1x1 plus dot 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 plus amnxn equals 0. So this system, and this is a homogeneous system, right? Because these constants are all 0. This is the homogeneous system of equations with coefficients in F. Now let S in Fn be the set of solutions to the system. So S is a subset of Fn because the solutions are elements of Fn. So this is a subset of Fn, and I claim that this is in fact a subspace of Fn. So the claim is S is a subspace of Fn. Well, technically, we have to show the 10 axioms. So if you look at, we need to show that S is a subspace, is a vector space over F, which means that, which means this, right? That it's a set together with operations. Well, we don't need to show that, but we need to show that there is an element 0 such that all these properties hold. Well, first of all, we can take the 0 element in V, which is Fn. So first of all, let's show that S contains a 0 vector. So notice that the 0 vector is an S because it's a solution to the homogeneous system. Okay, now if you think about it, do we need to check, let's go back here to property 5, do we need to check that for every, so this would be for every V in S, V plus 0 is 0 plus V equals V? Well, the answer is no. We don't need to check that. How come? Because if you have an element in S, it's already an element of Fn. And we know that whenever you take an element of Fn and add the 0 vector, you get that element. So therefore, if you take an element in S, the subset, and add the 0 vector, you're going to get itself, because that element of S is an element of Fn. So we don't actually need to check property 5. Now let's think about, do we need to check property 4, that vector addition is associative? Well, the answer is no, because, here's the proof. Suppose that you have 3 elements of S, U, V, and W. So suppose that U, V, and W are elements of S. Now forget about S. They're elements of Fn. And because they're elements of Fn, this equation is going to hold. And that's the proof. So we don't actually need to check property 4. What about property 3? That vector addition is commutative. Well, again, we also don't need to check that either, because if you have two vectors in S, they're elements of Fn, and we know that elements of Fn commute. I mean, one way to think about this is that properties 3 and 4 are really properties of the operation addition. They're not properties of the subset, right? And so since we're talking about the same addition operation, we don't need to check properties 3 and 4. And we don't need to check property 5 either. We do need to check that the zero vector is an element of the set S. Okay, what about properties 1 and 2? Do we need to check that in order to show that S is a subspace? Well, here the answer is yes, we do need to check that, because if you have a subset, it's not automatically true that whenever you add two elements of the subset, the sum is in the subset. And it's not automatically true that when you have a subset and an element in the subset and you scale it by some scalar, by any scalar, that result will also be in the subset. That's not true for arbitrary subsets. So we actually need to check 1 and 2. Okay, let's continue. Do we need to check property 6? Yes, we do. Because if you have a subset and an element in the subset, it's not automatically guaranteed that the additive inverse is in S. That there is an additive inverse in S, I should say. So we do need to check property 6. What about property 7? No, we don't. Because if you have an element in S, it itself is an element in V, and so we know that 1 times V will be V. What about property 8? No, we don't need to check that either, because we can just use the same argument that if you have A and B and F, and V in S, then V is in V, and we know this property holds. And lastly, what about the distributive property? We don't need to check that either for the same reason. So let's summarize what we have to actually do. We need to check that the zero vector in the space V is actually in S. There's something I'm sort of glossing over, which is how do you know that a vector space can't have more than one zero element, but that can be proven. So if S is a subspace of Fn, it must contain the zero element in Fn. Otherwise, it's not a subspace. So we have that in this example, that the zero vector is an S. And what else do we need to show? We need to show that the sum of two vectors in S is a vector in S. We also need to show that any scalar multiple of a vector in S is a vector in S. And we also need to show that each vector in S has an additive inverse in S. The in S part is really important. Because we know that the sum of two vectors in S is in Fn. And we know that any scalar multiple of a vector in S is in Fn. And we know that each vector in S has an additive inverse in Fn. But that doesn't mean that S is a vector space. In order to be a vector space, these things need to be in S. Okay, let's try to show this. So let's show, let's call this 1, 2, and 3. So for the proof of 1, we need to show that the sum of any two vectors in S is a vector in S. So let V say V1 through Vn, and W be W1 through Wn, let V and W be elements of S. So we want to show that the sum is an element of S. Well, what does it mean for V and W to be elements of S? It means that they are solutions to the homogeneous system. So then A11 V1 plus dot 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 plus A1 and Vn. Now notice that the Vi's are scalars, right? They're elements of the field. So we have this is equal to 0, and we have AM1 V1 plus dot 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 plus AM1 V AM1 to AMN Vn is equal to 0. And we also know that the same is true for the Wi's, that A11 W1 plus dot 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 plus A1n Wn is 0, all the way to AM1 W1 plus dot 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 plus AMN Wn is 0. Now what we want to show is that the sum, which is V1 plus W1, V2 plus W2, all the way to Vn plus Wn, right? That n-tuple, that is a solution to the homogeneous system. So we know that these two systems are satisfied, and so therefore, A11 V1 plus W1 plus dot 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 plus A1n Vn plus Wn is 0. Right? This is just obtained by taking the first equations of these systems and adding them. And similarly, we just do the same thing for all the other equations and get dot 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 A M1 V1 plus W1 plus dot 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 plus AMN Vn plus Wn is 0. And what that means is that V plus W is in fact an element of S. So that shows condition 1, that the sum of two vectors in S is in fact a vector in S. Now let's show condition 2, that any scalar multiple of any vector in S is itself a vector in S. So to do that, let C be an element of F and V be an element of S. Right? And with V being V1 to Vn. Now we want to show that the vector CV1 to CVN, that is a solution to the homogeneous system. Well, let's see what happens when you plug it in. A11 CV1 plus dot 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 plus A1N CVN dot 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 AM1 CV1 plus dot 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 plus AMN CVN. What does this equal? Well, in the first equation, we can distribute the C across. We can pull out the C and get that this is CA11V1 plus dot 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 plus A1NVN. And this is equal to what? 0. How do we know that it's 0? Because V is an element of S. And so therefore, this expression is equal to 0. This is C times 0, which is 0. And similarly here, in this last equation, it's CAM1V1 plus dot 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 plus AMNVN. And since V is an S, this expression is equal to 0. So this is C times 0, which is 0. And it's the same for all the other equations. And so therefore, CV is an element in S. Now the last one is that each vector in S has an additive inverse in S. So let's say that V, which is V1 to Vn, is an element of S. Right? Then is there a vector such that V plus that vector is the 0 vector that is also an S? Well, yes. Then W is, if you define it to be negative V1 to negative Vn, is an element of S because, well, we can take C to be negative 1 in condition 2, right? We know that any scalar multiple of V is an S, and in particular, if we take negative 1, then we get W is an S. So that's the proof. That's the proof that the solution set to a homogeneous linear system is in fact the subspace of Fn. Now let's record the fact that we really only need to show like 3 things, 1, 2, and 3, once we have that the 0 vector is an S. Okay. So let's record that as a theorem. The theorem says that if you have a vector space V, so let V be a vector space over F, then a subset U in V is a subspace of V if and only if the 0 vector is in U. That's the first one. And the second one is whenever U1 and U2 are in U, then the sum U1 plus U2 is in U. We also need closure under scalar multiplication. So if U is in U and C is in F, then CU is in U. And then the last one is if U is in U, then negative U is also in U. So this second condition is often called closure under vector addition. And this third condition is often called closure under scalar multiplication. Actually, this last condition is not really necessary because we'll see. So this last condition is actually not necessary because we'll show that in general, the additive inverse. So here, this negative u means the additive inverse of u. But it turns out that in general, the additive inverse of u, right, is equal to negative 1u. Negative 1 being the additive inverse of 1 in the field. And so actually, this last condition is covered by the previous one because you can take C to be negative 1. So in general, the additive inverse of U is by definition, turns out to be what you get when you scale U by negative 1. So actually, you only need to check these three things. These are the three things you need to check. And actually, when you look at books on linear algebra, right, that are introducing subspaces, this is often the definition that's used. That if you have a vector space over a field, or they might take, for example, Rn, a subset is a subspace if these three things hold. And now we see where this comes from. The conditions that these three things hold is exactly the condition that the subset is itself a vector space. Okay, I think that's already been a pretty long video. We'll take a look at some theorems in vector spaces. We'll prove some basic propositions. So for instance, why is the statement even true itself? And we'll take a look at some more examples of vector spaces. Okay, thanks.